For millennia, humanity never really got their musical intonations right. Until now.
So, you finally want to truly understand why some tones sound nice together and others don't, like in this snippet from the first episode of the Cleantone Temperament series. If you came here from this video or not, if you're into Cleantone Temperament or not, this is so fundamental for any intonation that you really should understand it. But not as in those half-baked so-called explanations floating around the internet, talking about our ears performing some lightning-quick calculations to decide if something sounds nice or not. No, here you will get the real truth, based on physics. The thing with physics, and the truth in general, is it doesn't need us humans. It just is. It's reality. The Earth would be spinning around itself and orbiting around the Sun just the same, no matter if we humans ever discovered, believed, or understood this, even if humans never existed. Likewise, sound waves are more or less in harmony with each other, no matter if anyone hears them. What I am trying to say is this: if your understanding of reality needs to involve some conscious being, human or otherwise, then you didn't really understand anything yet. Physics works perfectly fine without that. No calculating ears required. And, as you will see, we really don't need much from physics. Just two major insights, both of them so obvious and undeniably true that you might wonder why I even mention them. Here's the first one. Possible things exist. Impossible things don't. That's it. Can you see how this leads to nice and not so nice sounds? No? Let me help you with that. Here is a string. It could be a string of a piano, a violin, a guitar, or a vocal cord of a human. Sure, it's very idealized, assumed to be infinitely thin and whatnot, so that we don't get distracted by technicalities and understand the core principles. The main point is this: if it's hit by something like a hammer or a fingernail, it starts to vibrate, or to use the official word, it oscillates. The question is, how does the string oscillate? Well, if you remember the physical insight you just learned, the answer is simple: in every which way possible, but not in impossible ways. To find out what's possible and what's not, notice that the string is fixed at both ends. So any oscillation where these endpoints need to move is impossible. For starters, this immediately rules out any wave which propagates along the string, like a water wave, because in such waves, each particle moves all the time. Thus, the only contenders are so-called standing waves, which oscillate in place rather than propagate, like this one. So, yeah, it oscillates in place all right, but it is still impossible since neither the left end nor the right end stays put at zero. However, there are always points on such standing waves which stay put and never move. They are called the nodes of the wave. We just have to make sure that such nodes fall on the points where the string is fixed to the board. We can fix one end by forcing the wave to always start there, or in official language by adjusting the phase of the wave accordingly. But the other end is still all over the place. We can fix that by adjusting the length of the wave such that this end becomes a node too. In summary, and using all the official words, we have found that the only possible waves on the string are standing waves with phases and wavelengths such that both endpoints of the string are nodes of the wave. The first one fulfilling this condition is called the fundamental. The next has half the length of the fundamental. The next has 1/3. The next one has 1/4, and so on. Any standing wave whose wavelength is an integer fraction of the fundamental wavelength is possible. It looks a bit confusing, so let's move them apart a bit for demonstration purposes. But keep in mind that they and many more are all cramped onto the same string. Now, in music, we usually don't talk about wavelengths, but about frequencies. And at this point, most explanations on the internet suddenly jump from wavelengths to frequencies without missing a beat, saying that integer fractions of wavelengths obviously imply integer multiples of frequencies. And in our animations, we too let shorter wavelengths oscillate faster. But why should that be so? This is far from obvious and needs one more insight from physics. To approach this topic, first note that if wavelength and frequency are indeed inversely proportional to each other, then their product must be constant, since no matter by which factor the wavelength changes, the frequency changes by the inverse factor, and those factors of change cancel in the product. So, is this product really constant, and does it have any physical meaning? In other words, is it a tangible quantity existing in reality? To answer the second question, let's look at propagating waves for a moment. I know I just explained that only standing waves are possible. However, those standing waves are actually superpositions of waves that propagate along the string and are reflected back and forth at its fixed endpoints. Most of these superpositions cancel each other out, and in accordance with our first physical principle, only those waves survive which combine with their own reflections to form standing waves with nodes at the string's fixed endpoints. But I digress. Let's not turn this into a physics lecture. So, here are a few waves. The one at the bottom is the longest, and the two waves above have 1/2 and 1/3 of its wavelengths. We show wavelengths here as distances from one peak to the next, but we could just as well choose the distance from any other point to the next point with the same height. A wave is a periodical thing, and the wavelength is simply the length of the period. Now, let those waves move or propagate, to use the official word. And let's latch a bar onto the waves, for instance at a peak, to follow them. Let's stop right here and see how far the bar, and thus the waves, have moved. They all covered the same distance. For the bottom wave, this distance is one of its wavelengths. For the middle wave, the distance amounts to 2 of its shorter wavelengths, and for the top wave, that same distance equals 3 wavelengths. Note that they all moved with the same speed, since they needed the same time to cover the same distance. As we have just seen, that distance equals the number of waves times the wavelength, and so frequency enters the game, which by definition is simply the number of waves passing by per time. But now the product we were after has appeared, and we see that it is nothing other than the velocity of the wave. This is its physical meaning. So if that product is supposed to be constant, then the wave velocity must be constant. But is it? Well, let's look at our traveling waves again. Note that the same points of the waves stick to the bar at all times. This is because all waves travel with the same speed, namely the speed of the bar. By contrast, if longer waves would travel faster than shorter ones, then it would look more like this. And here is the situation if shorter waves would travel faster than longer ones. None of those last two situations is reality, though, otherwise our world would look and sound very different. Imagine the bass hitting your ears earlier than the treble does, because longer waves would travel faster, or vice versa. Everything would be out of sync. And the farther away from the source you are, the more time the faster waves would have to increase their lead. So not only would everything be out of sync, but it would be differently out of sync at every point in space. And with light waves, it would be even stranger. Imagine blue light reaching your eyes earlier than green light, and red colors lagging behind even further. Fortunately, our world is not like that, and it is indeed true that the velocity of a wave is independent of its wavelength. This is the second insight from physics I was talking about. It might seem so natural to you that you probably never even thought about it, almost as high up on the non-deniability scale as our first insight that only possible things exist. And it is very general. It is true for any kind of waves, be it waves on a string, sound waves in the air, water waves, or electromagnetic waves. For the latter, it is the famous speed of light. For sound waves is the speed of sound, roughly 343 meters per second. Of course, such velocities do depend on the kind of wave and the medium the wave is traveling through, but importantly, they never depend on the wavelength. Let's now come back to our standing waves on the string. They don't move forward at all. Nonetheless, multiplying their wavelengths with the frequencies of their oscillations makes sense for them too. And this product is the velocity of the underlying propagating waves, which combine to form all possible standing waves on the string. This velocity is just as wavelength independent as always, and therefore the frequency of a standing wave's oscillation is indeed inversely proportional to that wave's length. In summary, we have seen how two absolutely obvious fundamental insights from physics are all we need to understand. The first principle, that only possible things exist, implies that only standing waves with wavelengths being integer fractions of the fundamental wavelength are possible on a string. The second principle, that the velocity of a wave is independent of its wavelength, translates this to oscillation frequencies being integer multiples of the fundamental frequencies. These are called overtones or harmonics. The fundamental, also called bass tone, is the most important and usually the loudest tone. It determines the pitch. The overtones determine the sound. Different instruments add overtones in different volumes to their fundamental. This produces their characteristic sounds. Without overtones, no instrument would be distinguishable from another. The C of a trumpet would sound exactly like the C of a piano or a saxophone or that of the human voice. That would be a very boring world. Fortunately, every instrument, every human, every bird, but also every airplane or sledgehammer, all have their own sounds. So far, so good. We now understand the vibrations on a string. But how do they translate to sound reaching our ears? Well, when the string oscillates, it pushes the air molecules around it. In this way, the oscillations of the standing waves on the string induce corresponding oscillations of air pressure. These pressure oscillations then travel as propagating pressure waves through the air, and should we be around, we hear a sound. These sound waves have the same frequencies as the oscillations on the string which generated them. Thus there is a fundamental frequency, and overtones with integer multiples of that fundamental. This is most clearly represented as a so-called frequency spectrum, which displays the amplitude of each frequency. Here is an example with the fundamental frequency set, rather arbitrarily, to 110 Hz. Since we are here, let's get some technicalities out of the way. Note that amplitudes are given in decibel here, as is common practice. This is a logarithmic unit and might give the wrong visual impression of how quickly amplitudes of higher overtones really drop. The original unit for sound pressure is Pascal and shows much more drastically what's going on. Here is the same spectrum in millipascal. For those interested, Pascal measures the root mean square sound pressure. That's why it scales with the square root rather than linearly with the number of sources. So two identical incoherent sound sources are not twice as loud as one. They are only about 41% louder. If you want double the loudness, you need to add 3 incoherent sources, or much easier, use an amplifier to amplify the amplitude of the original source. Anyway, this is not important for us, and I don't want to drift into an engineering lesson, but I put the equations on the blackboard just in case. You can pause the video if you're interested. Otherwise, don't worry about it. This video is about understanding reality, not about the units we use to measure it. Nonetheless, for completeness, here is how to get from Pascal to decibels and why two identical incoherent sources are always 3 decibels louder than one. So contrary to a widespread misconception, 3 decibels is not double the loudness, but double the sources. Doubling the loudness means plus 6 decibels, all because of that root mean square nature of sound pressure. Again, pause the video if you're interested. Otherwise, don't worry about it and simply rest assured that the units on the vertical axis do make sense. From now on, we will always use decibels anyways, as this is what you are probably most used to. For us, it's not so much about how high the bars are on the vertical axis, but where they are on the horizontal axis. The reason why I explained overtone series and frequency spectra in such depth is that they are the only physical reason for euphony. They and nothing else control consonances and dissonances. How so, you may ask? How exactly do overtone spectra influence euphony? And then, string instruments aren't the only instruments in this world, are they? What about other instruments such as wind instruments? Do they all have such overtone spectra? Well, I'm glad you asked. These questions will all be answered in the next video of this series, so be sure to check it out. But for today, I have already taken enough of your time and probably stretched your attention span to the limit. So let's call it a day for now, and let's be content with the fact that we now understand the physics of overtones. And let's explore what follows from this in the next videos. At the end of our journey, we will arrive at Cleantone Temperament, and we will understand by purely logical deduction, based on the undeniable physical facts presented today, that this truly is the optimal intonation for the Western tone structure. For now, though, let's just enjoy how it sounds. As always in this series, I will play a well-known piece in Cleantone Temperament at the end of each video. And, as promised in the previous episode, this time around we will hear We Are the Champions by Queen, to demonstrate how well this intonation works even for rather advanced chord progressions and key changes. Enjoy the chords! As always, if you want to compare this to how it would normally sound, I've got you covered. I uploaded the exact same song played in standard equal temperament, links in the cards and in the description below. Let me know in the comments which one you like better, and be sure to watch the next video in this series. See you there.